In this lesson, we're going to look at and investigate the instantaneous rate of change. So the instantaneous rate of change is an average rate of change, but the interval between the x coordinates is going to continually decrease. So sometimes when we have a question, and this is sort of, this is what calculus is all about. Calculus is the math of the rate of change as we approach a certain value. So it's more about the approach than the value at that point. So let's say I wanted to find the rate of change at a particular point. So if I have a point P on this graph, I want to find the rate of change at exactly that point. So what we can do is we can pick a point that's a little bit further away, and we can find the average rate of change between those 2 points. And this would be the slope of the secant line between point P and point Q. If we wanted to have a little more accurate rate of change at point P, we can then move that point a little bit closer. So now I'm going to move it to R, and I'm going to find the average rate of change between P and R. And that would give us a better idea of the rate of change at P. I could move the point a little bit closer. So instead of finding the rate of change through Q, which I then brought closer to find the rate of change between P and R, I'm now bringing the point even closer between P and S. So as I move that point closer and closer and closer to P, my rate of change at P, so exactly at P, so instantaneously at P, is going to become more accurate as I get closer and closer to P. So we're still finding the rate of change between 2 points, but we're moving that point closer and closer and closer to P. And what that does is, as you remember, a secant line is between 2 points. So that is the average rate of change between 2 points. As we approach, as we bring these points closer and closer together, it then becomes a tangent line, which is only passing through 1 point. So this is also called the limiting value. And this is where we introduce limits. So if you think of a limit, if I pick a point that's further away from a point X, and I find the difference between that point and X, I am looking as that gap closes. So as H approaches 0, so we're looking at a gap of H. So as that gap gets closer and closer and closer to 0, so there's no room between those 2 points, that is going to become my limiting value. So a limit, which you do in calculus, we're not going to do it this way in MHF4U. We're going to use a different method, but that's where limits come from. Limit is a limiting value as you approach a point and you make that gap closer, smaller and smaller and smaller, you're going to eventually have the instantaneous rate at that point, or the limiting value at that point. So for example, let's say we wanted to find the instantaneous rate of change of a function given as h of t, and we want to find it at exactly 3. So my graph here. Maybe not. So we have a function that looks something like this. We want to find the rate of change at this point 3. So what we can do is we can pick a point that's further away. So I decided to start from the left side, and I picked a point at 2, and I am going to find the slope of the secant line between 2 and 3. And then I'm going to move that point a little bit closer, and I'm going to find the slope of the secant line. And I'm going to bring it a little bit closer, and I'm going to find, and I'm going to keep doing this until I start to get a limiting value or a constant value. So I want that delta y over delta x to start to become the same answer. And once I start to see that pattern, then I can say that's approximately the instantaneous rate at x equals 3. I could also approach it from the other side. I could start at 4 and do the same thing. So I could start between 4 and 3. I can move it a little bit closer, and so on. So the important part is the approach. Sometimes when we want to find the instantaneous rate of change, because you might say, well, why don't I just stick in that number? Why don't I just find it at 3? Well, that's fine in some cases, but a lot of cases that point is undefined. Maybe there is no answer at 3. Maybe there's a hole there. Maybe there's a vertical asymptote. So we want to approximate it by getting closer and closer and closer to it until we can say that's pretty good. That's a pretty good approximation at that point. So I'm going to start with h of 3. So I'm going to plug in h of 3 into this equation, and I'm going to find that value. I like to do my calculations just in an area that's maybe below the table, so I save some room. So if I put in h of 3, I get 32.9. And then I'm going to do it with 2. h of 2 works out to be 32.4. So when I'm finding my delta y, I'm finding h of 3 minus h of 2. So I'm doing 32.9 subtract 32.4, and that works out to be 0.5. My delta x is 3 minus 2, which is 1. And my delta y over delta x is 0.5 divided by 1 is 0.5. So my rate of change between 3 and 2 is 0.5. Then I'm going to bring that point a little bit closer. So I'm going to find the value of h of the function at 2.5. And that works out to be 33.875. So then I'm going to do h of 3 minus h of 2.5. So I'm doing 32.9 subtract 33.875. That works out to be negative 0.975. Delta x is 0.5, 3 minus 2.5, and then I will divide delta y divided by delta x, and I get negative 1.95. So these two rates are very different, so I'm going to keep going. So I'm going to move that point closer to 2.9. I'm going to sub that into the equation, and I get 33.291. Then we're going to do h of 3 minus h of 2.9. And that works out to be 0.391. Delta x will be 0.1. We'll do that division, and we get negative 3.91. So still quite different. Negative 1.95 and negative 3.91 are quite different, so we're going to move it even closer. We're going to move it to 2.99. 2.99 gives me, try to use as many decimals as possible because you'll get a more accurate result. So we're going to do h of 3 minus h of 2.99. That works out to be negative 0.04351. Delta x is 0.01. And then when I do that delta y over delta x, I get negative 4.351. So that's starting to look a little bit closer. I've got negative 3.91. I've got negative 4.35. Starting to get a little bit consistency there. I'm going to do one more at 2.999. That works out to be 39.9044. I'm going to do h of 3 minus h of 2.999. And that works out to be delta x is 0.001. We do the division. I get 4.345. So now I start to see some consistency. I've got negative 4.3 for both of those results. When I go to the 100th place, it's a little bit different, but it's a pretty good approximation. So I might stop there. If I wanted to check one more interval, I could do 2.9999, but I'm going to say that's a good approximation. I'm going to say it's approximately negative 4.4 meters per second are the units. So I just rounded that. So that's a good approximation. So how many intervals do you have to do? There's no definite number of intervals. What the most important part is that you are showing that you are approaching the value and that you are going to show some consistency in the answer. In delta y over delta x, you're going to start to see a consistent value, and that's the most important part. Okay, so let's go back to that hot tub example. So we have the hot tub with a volume given as 1 over 9 times 120 minus t to the power of 2, and I want to find the instantaneous rate at 60 minutes. So as we said before, you can approach 60 from either side. I decided to approach it from the right side. You could also approach it from the left side. So you could go between 59 and get closer to 60, or you could start at 61 and get closer to 60. I decided to go from the right side. So I'm just going to do my calculations down here. So I've got V of 60 works out to be 400, and V of 61 works out to be this value. So I'm going to do V of 61 minus V of 60, and that works out, if I subtract those two numbers, it works out to be negative 13.22. Delta x is 1, and so the rate of change between 61 and 60 is negative 13.22. Then I'm going to get a little bit closer, so I'm going to do the volume at 60.5. And then we'll do volume at 60.5 minus volume at 60, and subtract those two numbers. Delta x is 0.5, and that works out to be negative 13.278. So that's a pretty good approximation, but I'm going to go even closer, and I'm going to do V at 60.1. Plug that in. So we'll do volume at 60.1 minus volume at 60, and we get this result. Delta x is 0.1, so if you make that division, we get 13.32. And I'll do one last one at 0.01. So like I said, there's no definite number of intervals. I just want to show as much consistency as I can. So V of 60.01 minus V of 60. Delta x is 0.01, and that works out to be 13.33. So 13.32 and 13.33 are very close. So that's a very good approximation of the instantaneous rate of change at exactly 60 minutes. The bathtub or the hot tub is losing minus 13.33 liters per minute.